I'm Vassili Karanassios. I'm with the University of Waterloo in Ontario, Canada. And I'm a chemist by training, but I'm also a co-founder of a degree program in Nanotechnology Engineering at the University of Waterloo. My key research vision is to bring the lab to the sample. We have to do it one at a time, of course, but the vision is to be able to bring an instrument to the lab, to the sample, rather than bring the samples to the lab as is currently done. Sensing has been around for a long time, and people have designed sensors that will do pressure, that will make pressure or temperature measurements or pH measurements. We want to take it one level up, something that requires some more complex instrumentation to be able to make the physical or chemical measurements that are required, let's just say, to monitor water quality. I come from Ontario, and the word Ontario means shiny waters. In Ontario alone, there's 250,000 lakes, more than 1,000 kilometers of rivers, and we also have the Great Lakes surrounding us. So water is a key resource for us that has to be protected, it has to be monitored. Many areas in Ontario, they're very remote. That is to say, you don't have to go to 7 time zones away to find a location where there's no power, where there's no wireless, things that we take for granted. So we have to design these micro instruments in a way that will be energy autonomous. But as we miniaturize systems, we'll lose a little bit of the selectivity. In many cases, we'll lose a lot of the selectivity. So we have to look at ways of looking at interference effects. How would we resolve this? And in my research group, we address them using artificial intelligence, neural networks, and more statistical methods, mathematical methods, if you will, such as partial least squares. The problem is far from having been solved or from being solved. We haven't had any systems that we can do field trials, but at the beginning we have to design the systems in a way that one will contemplate a few years from now field trials in terms of the energy autonomy, in terms of wireless capability. In many places in Northern Ontario, things that we take for granted, such as wireless capability, it really is not there. We're trying to see how we can make the power budget so that it will be as energy independent as possible, in that we're trying to find ways to minimize the power that is required. The other question that we address is, do we have to have the systems on all the time? Can we afford to have discontinuous operation, such as, for example, let's just say one is interested in measuring pressure, atmospheric pressure, or temperature, or water temperature. Do we really need to make 100 measurements every second? So we can wake up the system, make the measurement, put it in standby mode, and that will conserve energy. And then, of course, where do we find the energy? The obvious answer, of course, it will be solar, but we have to keep in mind that the sun doesn't shine all the time, and there are also cloudy days. Most people will use energy harvesting and energy scavenging to mean the same thing. To us, energy harvesting, if you go to the dictionary, harvesting is when you harvest something such as a crop. But scavenging, if you look again at the dictionary, will say you go and find something that has already been used or discarded. And people have been using, let's just say, solar calculators for a long time. So a lot of the light, the indoors light, it's been unused. So this being scavenged to power the calculator. So there are precedents for this. Seiko several years ago had a watch that was powered by the human body, by the heat of the human body. So that is energy, again, that is being wasted, and one can scavenge that energy. So to us, there's a clear distinction between harvesting, such as sunlight from the outside, or scavenging, something that has already been used, discarded. Another example that is obvious is air conditioning. Some of us like the air conditioning to keep our places cooler, but on the outside, we generate a lot of heat that's being discarded. That heat can be harvested or scavenged, a better expression, so that we can power things that need to be powered. So it doesn't have to be anything that is out of the ordinary. Mm-hmm. We just have to be inventive and creative. We rely on developments that come from the outside, from commercial developments. We try to use single board computers, things that will be lightweight, that will take very little power. But although this is a great area, we're just not directly involved in it. We're just trying to use as much as possible things that have already been invented by others and have been commercialized. And our version is we have a little instrument, and then that has an embedded computer. So all of the computing is done, or most of the computing is done locally. And then it has a link, in some cases via satellite, to a location where you have access to the web and everything else, where power is not an issue. Right now, the biggest hurdle is money. And it's kind of difficult sometimes to convince people to put their hands in their pocket. Some people think it's applied research. Some people think it's just too far-fetched. It's too blue sky ideas. So it's kind of difficult to convince people. Luckily, we got some companies convinced, like IBM through the Green Planet Initiative, or Smart Planet Initiative, I should say, and through the watershed, looking at water quality issues, that is helping a lot. Water is going to become a key commodity, and people say that water might be more important than oil in the future. There are many parts of the world that don't have clean water. Billions of people are being affected. And according to the World Health Organization, 35% of deaths worldwide are due to poor water quality.